Chemical Foundation of Life, Chapter 2, Part 5. pH buffers acids and bases. Oh my. pH is essentially a concept based on a mathematical formula, an equation if you will, about how much of positive and negatively charged ions are in a solution. But those ions are very special. They're what we call positively charged hydrogen ions and negatively charged hydroxide ions. Notice the chemical equation in the middle of this slide. We have one molecule of water breaking down into one hydrogen ion and one hydroxide ion. Remember, we're illustrating that these are ions with the plus and the minus superscript sign next to the abbreviation of these atoms or these structures. So if we take a look at how much hydrogen ion and how much hydroxide ion we have present, we come to the concepts called acidity and alkalinity. We have hydrogen ion concentrations that we can measure and hydroxide ion concentrations that we can measure. And the more hydrogen ions we have in, say, a beaker of water, the more acid, or what we call acidic, that water will be. The higher the concentration of hydroxide ions, then we would describe that solution as being more alkaline or basic. Well, that's all well and good, but what does all that mean? Well, if you've ever had a lemon or a lime, you know that one of the characteristics that you'll taste, one of the unique flavors or sensations that you'll have when you bite into a piece of lime or lemon, is that it's sour. Well, that's the general characteristic of an acid. It makes your mouth water, and it's going to make your mouth pucker because of the high hydrogen ion concentration. On the other hand, if you've had the unfortunate introduction of soap in your mouth, or maybe baking soda, or something called milk of magnesia, that's going to give you a very different sensation in your mouth because those are alkaline or basic materials or solutions. The comparison or the distinctive differences between acids and bases is part of a foundation for organisms here on Earth. And in fact, we can actually calculate based on how many hydrogen ions versus how many hydroxide ions are present in a solution or in a material, and determine that concept that we call pH based on a mathematical formula, which is illustrated in its most simple form in the middle of this green box on the left. Lowercase p, uppercase h. It has to be in that format because that is a mathematical abbreviation for the letters and numbers and such that are on the right-hand side of the equal sign. The right-hand side of the equal sign is what a chemist possibly could use, or what I've been told for many years, chemists say for biology students, that's good enough for us to understand that pH, or acidity or alkalinity, is based on the negative log base 10 of the hydrogen ion concentration. Now, that's actually what that whole phrase means, or that whole part of the equation on the right-hand side of the equal sign actually says. The H stands for hydrogen, that particular element. The plus sign next to it indicates that it's the ion of hydrogen. The square brackets is actually the chemist's abbreviation for concentration of. So on the right-hand side, that's hydrogen ion concentration of, and then you're going to do a mathematical manipulation of that number of the concentration of hydrogen ions and use the negative log base 10 to get kind of a measurement. For a mathematician, we're going to abbreviate that using the P, which stands for negative log base 10, and the H that stands for concentration of hydrogen ions. When you go through the actual calculations, which chemists actually use a formula or mathematical formula that's more detailed, it's going to take into account not only hydrogen ion concentrations, but the actual equation that's used to calculate pH also will take into account hydroxide ion concentrations. And you wind up with essentially an exponent. Log 10 of 1 times 10 to the minus 7 is minus 7, but notice we're going to negate that. So the negative of the negative is a positive, and so we get a whole number 7. We can do these calculations for various types of substances, starting with bleach, going all the way down to stomach acid or gastric juices. When we go through those calculations, we wind up with a range of numbers. There are no unit values. In other words, it's not milligrams or milliliters or units of any kind. These are numbers. And we wind up with a range of numbers from 0 to 14. This is what we call the pH scale. And different substances, especially related to biological systems and organic systems, will fall somewhere between 0 and 14 on this pH scale. Oftentimes pH scales are illustrated with colors just to give students an idea of the differences in these substances. So here we have items like gastric acid up to coffee, even urine, and those are going to have small numbers, which actually mean they have high concentrations of hydrogen ions, or we call these acid solutions. So any material that has a pH of less than 7, we describe that as an acidic solution. On the other half of the scale, if we have substances that have a pH greater than 7, looking at seawater, baking soda, soapy water, and bleach, we call those alkaline or basic solutions. If we wind up with an even number, equal number of hydrogen ions and hydroxide ions, then we say that the pH is neutral at 7. Human blood pH is pretty close to 7. Human blood pH is between 7.35 and 7.45 and is maintained for the most part, unless some kind of pathology or disease is occurring. It's maintained at that very tight restricted range of 7.35 to 7.45. So pH of 7 considered neutral, and that would be distilled water. pH less than 7, that would be an acid. pH greater than 7, it's going to be considered an alkaline. And of course, the further away from the center, the further away from 7 that we get, the more extreme the acid or the base in terms of its ability to cause some kind of change to whatever it comes in contact with. Substances called buffers are important in biological systems because buffers help to moderate changes in pH. We have some very special types of buffers in our body that take advantage of the CO2 or carbon dioxide that builds up when our cells metabolize, when our structures in our body are growing and consuming food and producing waste products. So CO2 is one of those sort of waste products from metabolism of our cells, and some of that CO2 actually dissolves in the water in and around our tissues and in our cells, and has a buffering capability when it combines with some of the water. That buffering capability of these other molecules, the carbonic acid in the middle and the bicarbonate that's on the left, actually help to moderate pH. So we don't see extreme changes in pH when there's a buffering system available, which is good. We don't want those extremes. We want to keep a nice, even, tight range and control of pH in an organism.